Welcome to the class. In this class, we will discuss about the shear force and bending moment diagram for a overhanging beam. Let us take one example for this. We have a beam of span 6 meters, which is supported as shown in the figure. So here it has support, and here we have one more support. So a beam is said to be a overhanging beam when a part of the beam is hanging outside the support. Then only we call it as overhanging beam. Here this beam is subjected to point loads, which has been shown in this figure. So the distance between these are, like, from here to here it is 2.5 meters. Then from here to here it is 1.5 meter. Again from here it is 1 meter. From here to here this is again 1 meter. So let's mark these, like this is 2.5 meter, this is 1.5 meter, this is 1 meter over here, and this is 1 meter over here. And the intensities of load or point loads, this is 20 kilonewton here, it is 20 kilonewton, here it is 15 kilonewton, here it is 10 kilonewton. Let us mark it as this is point A, this is point B, point C, this is point D, and point D. So if you want to calculate the shear force and bending moment diagram for a overhanging beam, first I should know, like, the sign conversions which we need to follow to determine the shear forces and bending moment. You can note it down, like the sign conversion for shear force diagram. So if you are calculating shear force, from the if you are calculating shear forces from the left side, from this side, upward forces we treat as positive and downward forces we treat as negative. Upward forces we treat as positive and downward forces we treat as negative. If we are calculating shear forces from this end, from the right hand, upward forces are like negative, downward forces are positive. Here upward forces are negative and downward forces are positive. This is the sign conversion which we follow for the shear force diagram. Next, for bending moment diagram, the sign conversion is like this. If you are considering our beam from the left end, for example, if I'm considering from this end, then if there is a force like this, for example, this force is P and the distance is X. This force creates a moment that is P into X. This is the moment, bending moment. So this Px force acts in which direction? It acts in the clockwise direction. So clockwise we treat as positive. with it as a positive in the sense this force P creates a sagging moment. This force P creates a sagging moment of the beam. So that's why we call it as positive. Again, if in the same example, if we are considering from the left side, in the sense from this side, if the forces are applied in this direction, so this is the force P, and if this is the distance x, this force into distance Px will create moment. So it creates in anti-clockwise direction. So we consider this as negative moment. Moment as negative moment. Here we consider it as a positive moment. So here it is in clockwise direction. It is in counterclockwise direction. It is in counterclockwise direction. It is in clockwise direction. So this is the sign conversion which we follow. So this is for like when we consider forces from the left side. If we consider forces from the right side, then the sign conversion will be like this. For example, if you have a beam like this, if it is subjected to a point load here, if this is the distance x, this is the force P, then this force into distance will give you the moment. It tries to bend the beam. It tries to bend the beam in this direction, in the sense in counterclockwise direction. So it creates a sagging moment. It creates a sagging moment. Sagging we consider as a positive. So it is a positive moment. So it is a positive moment. If you consider from the right side, the counterclockwise will be the positive. Counterclockwise moment is the positive. Again, if the beam is like, if we are considering from the right side, if the force is like this force is let's call it as P, and this is the distance x. If this is the distance x, this P into x will give you the moment. Force into distance will give the moment. So it bends the beam in the clockwise direction. In other sense, it creates a hogging moment. It creates a hogging moment. So hogging we consider as negative. So when we consider the moment from the right side, this sign conversion I need to follow. When I consider the moment from the left side, I need to consider this sign conversion. So I hope so you are clear with this. If you have any doubt with this, you can comment in the comment box so that I can replay for you. Next we'll calculate shear forces for this. We'll calculate shear forces for this. Before calculating the shear force, I should know what are the reaction forces which are generating here. I should know what is the reaction force at the support A, and I should know what is the reaction force at the support D, RD. So RA and RD are nothing but support reactions. How to calculate these support reactions? So if you want to calculate the support reaction, I should take moment about a point. So I can take moment about this point, or I can take a moment about this point. Let's go with this point, so that it will be easy for us. Summation of moments about point E is equal to 0. From this point, we are taking the moment. So we are fixing, in other sense, we are fixing this point. Now, here we have RA force. This force RA force and perpendicular distance to this point will give you the moment. So I can write RA into the distance. This is the force RA, the distance is 6 meters. So now the main problem is whether it is a positive or negative. Whether this is positive or negative. How to determine? Like as I told you, The sign conversion for this is like if you have a being like this, if the force is applying like this, if it is creating an clockwise movement over here, it creates a sagging moment. Sagging is nothing but positive from the left side. So this is a sign conversion which we follow. So this should be plus. Now here it creates negative movement. Same again as I explained earlier. So if this was the beam, if this was the force, if it creates a moment in anti-clockwise direction, which it is negative. So be careful while you are taking the sign conversion, because I am considering from the left side. I am considering from the left side. If I am considering from the right side, these are the sign conversion. This is from the right side of the piece. This is from the right side of the piece. But in this problem, I am considering from the left side. From this end, I am considering the moment. Clear? So here it is negative because it is in counterclockwise direction. So minus 20 is the point load and its perpendicular distance to this point is 1.5 plus 1 plus 1. So it is 3.5. Next here we have 15 kilonewton which is acting at point C. So I can write it is again minus because it is again creating an anti-clockwise movement. So it is again 15 into the distance is 2 meters. Next here at D we have a reaction force RD. Now RD, whether it is a positive or negative, again same. It is creating a clockwise movement, so it should be positive. RD into the distance is 1 meter. Again at point E, we have negative because it is creating a negative moment. 10 into the distance at this point is 0. Or you can say this will be 0, which is equal to 0. I hope so it is understood, right? Because here this is the force 10 kilonewton and the distance is E. E in the sense at this point itself, the distance is 0 here. If you see here RD into 1, this is the force, RD is the force and this is the perpendicular distance. If you are considering from the point C, 15 into distance is 2. But we are considering at this point itself, 10 into the distance is 0 because here there is no perpendicular distance, so it is 0. Better you can write 10 into 0 or you can write 0 or you can leave it, no issue in this. Now I need to simplify this. If I simplify this, 6RA plus RD minus 6RA plus RD minus, so if you multiply with this, you will get 70 here minus 15 to the 30, which is equal to 0. If you simplify, we will get 6RA plus RD is equal to 100. This is the equation number 1. So next, the second equation, that is to get, like here we have two unknowns, right? Here we have two unknowns, RA and RD. When we have two reaction, I should know two equation. Then only I can calculate. Two unknowns, two equation, then I can solve easily. I can determine the reaction forces at A and D. So this is the reaction force. Like first equation to calculate the reaction force. 6RA plus RD is equal to 100. Next, second equation, how we can calculate here? The second equation can be like upward acting forces should be equal to downward acting forces. Downward acting forces. Okay. So here, if you see in this beam, upward acting forces are these two, RA and RD. These are the two upward acting forces. So I can write here upward acting forces are RA plus RD, which is equal to, what are the downward acting forces we have here? Downward acting forces here we have 20 kilonewton, 15 kilonewton and 10 kilonewton. So I can write 20 kilonewton, 15 kilonewton and 10 kilonewton. Upward acting forces should be equal to downward acting forces. So I get here RA plus RD is equal to 45. So this is my equation number 2. Or you can simplify this as RD is equal to 45 minus RA. This is equation number 2. Now substitute this equation number two in 1. If you substitute equation number 2 in equation number 1, you will get RA is equal to reaction at support A is equal to 11 kilonewton, and RD is equal to, you will get 34 kilonewton. Take your time and calculate, you will get these two answers, RA and RD. So this is how we can calculate the reactions at the support. Now then we'll move to the shear forces. How to calculate the shear forces at the each point. How to calculate shear forces at each point, we will see now. Okay. Now here shear force at this point again will come from the left side. Again the sign conversion for this. If you have a plane XX, from the left side upward forces are positive, downward forces are negative. This is the sign conversion for shear force diagram. Like here, upward force. Here we have RA is equal to, we got RA as how much, 11 kilonewton, and RD is equal to, we got around 34 kilonewton. This is the reaction forces which we have calculated. Now I need to calculate the shear force at A. Shear force is nothing but summation of forces which are acting towards the right or left of a beam. Now we are coming, here we are here we are treating from the left side. So reaction force, shear force at point A. At this point we have a reaction force as 11 kilonewton. So upward acting forces are positive, 11 kilonewton. At point B, shear force at the point B, I can say the forces which are acting towards the left side. So what are the summation of forces which are acting towards the left of this? So here we have to the left of this we have 11 kilonewton, plus here we have 20 kilonewton. Now whether it is a plus or negative, because downward acting forces are nothing but negative. So I need to consider here it as negative. So negative 20 kilonewton. So it will be minus 9, I think, right? Minus 9 kilonewton. Next, shear force at point C, at this point. From this point towards the left, towards its left, what are the forces we have? Like we have this point load 11 kilonewton. This is positive because upward acting forces are positive, and downward acting here we have minus 20, then we have minus 50. So if you simplify this, you will get I think minus 24. Next, at point D, from the left of this, from the left of D we have this plus 11 kilonewton, minus 20 kilonewton, minus 15 kilonewton. Again here it is plus because it is acting upward. Upward is plus, so it is 34. If you simplify this, you will get At the point D, you will get around 10 kilometers. That is plus 10. Now at point E, at point E, at shear force at point E is equal to, at this point, at point E, again you can calculate plus 11 minus 20 minus 15, again minus, sorry, plus 34 minus 10, which is equal to, we'll get here as, again I think so, this 0. This 0. Yes, this is how I need to calculate, how we need to calculate shear forces at each point. So shear force at point A is 11. So we will draw the shear force diagram by using these data. So here I should know the shear force at point A. I'll write here. Shear force at point A is 11 kilonewton. At B it is minus 11, minus 9. At C it is minus 24. At D it is 10. At E it is 0. Now we'll draw the shear force diagram for this. Now we'll draw the shear force diagram. To draw the shear force diagram, first I need to take a reference line. This was a reference line. Again, then I need to take some appropriate scale. Then I need to point these, I need to mark these points. This is A, this is point B, this is point C, this is point D, this is point E. Now, shear force at the point A, it is 11 kilonewton. Shear force at the point A is 11 kilonewton. So I need to mark that, like you can take 11 centimeters or 5.5 centimeters, somewhere here. Clear? So this is the shear force which is acting at this point A. And between these point A to B, we don't have any forces between A to B. So we get a constant horizontal line. Next, at the point B, we have, at the point B, we have minus 9 kilonewton force. At the point B, minus 9. Minus 9 in the sense, this is zero line. So minus in the sense, it approximately here, minus 9. This is minus 9. This is, here it is around 11, right? It is 11. Now, here from this point to this, we have the minus 9 at point B. Then at point C, it is minus 24 kilometers. Before that, between B and C, there is no loading. So I need to draw a horizontal line. But at the point C, I have loading of minus 24. How much? Minus 24. So I need to draw minus 24 somewhere here, minus 24. Let us point here, minus 24. And here I need to draw a line. Clear? Again, from C to D, from this point to this point, C to D, I don't have any force in between these. So I get a straight line over here. I get a straight line. At a point D, I have a force of plus 10 kilonewton. Here I have force of 10 kilonewton. So I need to draw this plus 10 in the sense this is 0. Somewhere here we get a plus 10. For example, this point denotes 10 kilonewton plus 10. Next, I need to draw this line. Next, between D and D, I don't have any force. So again, it will be again here. It will be between D and D. No force. At the point E, the force is zero. At the point E, the shear force is zero. So make it as this. So this is the shear force diagram. This is the shear force diagram for the given overhanging beam. So mention the values here. It is 11 here. It is -9. This will be -9. This will be -4. This will be 10 here. This is the shear force diagram. So now we will calculate the bending moments for the given overhanging beam. So that so to calculate the bending moment, I should know what are the force and perpendicular distance. Force and perpendicular distance. Let's arise these things. Now we'll calculate bending moment at these points. Now again we are considering from the left side. So bending moment at A. Bending moment at the point A will be like this. I am calculating moment about this point. Clear? So at this point, I have a force of how much? 11 kilonewton. And I should know this is the force into perpendicular distance. I should know the distance in the sense at this point itself I am calculating the moment. So distance is 0. So I am getting 0 kilonewton meter force into distance. Next, bending moment at a point B, at this point. So if I want to calculate moment about this point, I should know what are the forces or what are the moments which are acting towards the left of this, towards the left of B. So here I am having 11 kilonewton. This is the force, and this is the perpendicular distance. This is the 2.5 from this force, this perpendicular distance, 11 into 2.5. Now the doubt is whether it is a positive or negative. Again, you need to go for this. Like if this was the beam, if this was the force, then clockwise we consider as positive, and if this was a beam, if this was a force, this counterclockwise we consider it as negative. This is the sign conversion which we follow when we are calculating bending moment from the left of the beam. Yeah, I hope so it is clear. Right, okay, fine. So at this point, towards the left, we have 11 kilonewton into perpendicular distance. This is the again positive. Again here we have minus 20 because it is creating in which direction? Counterclockwise we can consider as negative. So 20 kilonewton into, at this point itself I am calculating the bending moment. So the distance is 0. So better you can take it as 0. So you will get bending moment at this point 11 into 2.5. It is around 27 kilonewton meter. Now at a point C, bending moment at a point C. At this point I need to calculate bending moment. So towards the left of this point, what are the forces? Those forces create the moments. Those things I need to consider here. First force is 11 kilonewton, positive 11 because it is clockwise. 11 into this force into perpendicular distance till this point C, 2.5 plus 1.5, 2.534. 11 into 4. Next minus, it creates anti-clockwise movement. So minus 20 into, at this point 20 into 1.5. And the next minus here 15. Again it is creating anti-clockwise movement, minus. At this point itself I am calculating the moment, so the perpendicular distance is 0. So if you calculate, if you simplify, you will get 4 kilonewton meter. 4 kilonewton meter. Now at a point C, at this point, towards the left of the point D, what are, how many moments we have? Like this moment, this force, clockwise force into the distance from here to here, it is 2.5, 1.5, 3, 4, 5. So total distance is 5. Next, this force 20 kilonewton into the distance is 2.5. Next, minus 5 minus, again it is creating anti-clockwise moment. So minus 50 into 10 into 1. Again you can write plus this force adding into the distance at this point itself I am calculating. So adding into 0, it will be 0. So if you simplify, you will get around here minus 10 kilometers. Next, at the point E, at the point E, at this point, if you simplify like this, you will get at the point E as 0. So these moments will write here. At point A, it is 0. At point B, it is 27. At point C, it is 4. At point D, minus 10. At point E, it is 0. So if you have confusion how the 0 has came here at point E, let's calculate for that also. At the point E, bending moment point at point E. Moments from the left of this. So first we have the force 11 kilonewton, which is acting in clockwise direction. So 11 into the total distance till this 2.5, 1.5, it is 4, 5, 6. Total distance is 6 here. Okay. Next, minus here we have 20 kilonewton because it creates an anti-clockwise moment. So 20 into 3.5. Then we have minus 15 into 2. Next, plus 34 into 1 because it's creating clockwise moment. Next, we have minus 10 into 0, so 0. If you simplify, you will get 0. So this is the moment, moment about E, bending moment at point E. Now we'll draw the bending moment diagram for the given overhanging by using these values. So for this, first I need to draw a reference line. Then I need to mark the points like this is A, this is point B, this is point C, this is point D, this is C. Now here at point A, bending moment is 0 kilonewton meter. So at point A, it is 0 kilonewton meter. At the point B, it is 27. So here 27. So in shear force diagram, wherever there is a point load, like we have drawn a horizontal line. Like if you draw the horizontal line in the shear force diagram, in bending moment diagram, it should be inclined line. It should be inclined because why it is because the slope of shear force is equal to bending moment. The slope of shear force diagram is equal to bending moment diagram. That's why if we have a horizontal line in the shear force diagram, here we get the inclined line. Next, at point C, we have 4 kilonewton meter. 4 kilonewton meter. This is the point C. Here we have 4 kilonewton, somewhere approximately here 4. Again, here I need to draw which line? Again, it is inclined line, because from B to C, if you see the shear force diagram, there we have a horizontal line. So here we get the inclined line. Next, at a point D, at a point D, at the point D, we have minus 10 kilometers. So minus 10 in the sense approximately here. This is minus 10. Again, from point C to D, if you see shear force diagram, there we have a horizontal line. So we are getting an inclined line over here. Next, at the point E, the shear force, the bending moment is 0. At this point, it is 0. If you see the shear force diagram between point D and E, we have a horizontal line. So here we get inclined line. This is how we need to draw the bending moment diagram. Bending moment diagram. Now, there are the two things. There is one thing which we need to observe here, that is somewhere here the sign of bending moment is changing, like from positive to negative. Positive to negative. Sign of bending moment diagram is getting changes here. The point where the bending moment diagram changes its sign is known as, this point is known as point of contraflexion. Point of contraflexion. What is this point of contraflexion? How to calculate this point of contraflexion? These things we will see in the upcoming videos. Like I'll come up with the new numericals on the shear force and bending moment diagram. Like if you feel like it helps you, like if you feel it helps you, you just share this video with your friends. Thank you for watching. The next video will come in soon.